Okay, let's try take two. So we've got, this is about homework 1 for CET236 in spring 2022. And the link that you need is in Blackboard, but the actual problem sets are over in WebWork. So the link here to fundamentals should actually take you here. And I think I've set it now to close on February 5th, so you should be good. And it should be also showing that in Blackboard as well. Doesn't matter, the one that matters is WebWork, so provided you get it done by then, it's fine. So problem 1, as I said the first time around, this is take 2. Wire has a current of 30 microamps flowing through it. How long does it take for a charge of 45 coulombs to pass through the wire? And the trick here is we've got to relate microamps to coulombs and get a time out of it. And the relationship between amps and coulombs is straightforward. 1 amp is 1 coulomb per second. Okay, so let's just have a look. We've got 30 microamps and 45 coulombs. Let's turn that around. There we go. So we have 30 by 10 to the minus 6, and that's amperes, which is equal to 30 by 10 to the minus 6 coulombs per second. And we're after an answer of seconds. The other number we have is 45 coulombs. Right, so how do we do that? Well, the relationship is we're going to have coulombs per second times seconds equals coulombs. Just simple as far as the units are concerned. And so what we need is to find the seconds, we need to go from we need to divide both sides by coulombs per second. So we get coulombs divided by coulombs per second, and that's going to give us our answer. So the coulombs we have are 45, or that we want to accumulate is 45, and so that should give us the answer we're after. And I don't know what the best way to do that is. Let's go here and just say we've got 45 divided by 30 by 10 to the minus 6, and that gives us that number. And I think that's what I had before. A tricky thing about WebWork is you have to usually give it units as well, right? So in this case, so let's just, I'm going to see if I can paste that there, right? So there's, but I need to make sure when I put the answer into WebWork that I give it in seconds, right? And the sorts of units that WebWork is going to require: S for seconds, A, capital A, for amperes, capital V for volts, and it doesn't expect you to be able to type a capital omega, so for resistance, ohms, it's expecting OHM. It's going to need capital W for watts and capital J for joules. They're the main ones. There might be some others that we come across, but they're the main ones that we're going to use. I think their frequency might also be a thing. Okay, so that's problem 1. Let's go back. Right, so I'm just going to preview my answers, and that looks good, and then I'm going to check my answers, and it says correct. All right, let's just see what happens if I don't have the units. Right, it's going to say incorrect, and your answer doesn't look like a number with units. And if I give the right units but the wrong number, it's just going to say incorrect. Okay, so it doesn't matter how many times you try in web work. You can try as many times as you like to get the right answer. So just don't get frustrated if you try lots of things and nothing's working. Come and talk to me. Either I'm happy to answer questions on Discord. That's usually the easiest. I don't necessarily answer immediately, but I do answer. Right, but if you're getting the correct information, then you should get all green. Right, here's problem 2. Excuse me. A 6-volt battery provides 1/4 of an amp to operate an electric bulb. How much energy does the bulb dissipate in 3/4 of an hour of operations? Your answer should be in joules. Okay. So again, this sort of problem is mostly a unit conversion problem. Right, so let's just put that down here. Here's problem 2. Okay, problem 2. A 6-volt battery. So one thing we can say is that the battery is providing 6 times 0.25, right? Remember, P equals VI. So there's V6, right? And what's 1/4 of 6? That's 1.5. And our answer, this is in watts. Okay, and now the question is, how much energy, right? And I think the question might be a little bit misleading, because W is not usually what we use for energy. I'm not sure why it's set up like that. But so the question is, how do we get watts to joules? Well, again, watts are joules per second, right? So in order to get and unfortunately sometimes OneNote goes strange on me. So as I said, watts are joules per second. So in order to get joules, we need to multiply our watt figure by the number of seconds. Now we've been given it the time in hours. So the time, I'm going to call it S, is going to be equal to 0.75 times, now the number of seconds in a minute is 60, and the number of minutes in an hour is also 60. Right, so that's going to be 0.75 times 3600. Okay, so to get our answer, now we need to say 1.5 times 0.75 times 3600 equals the number we're after. And I'm just going to go back and do that on Google. So 1.5 times 0.75 times 3600. Right, which is our 4050. So one thing you'll notice is the numbers I'm giving you now are different from the numbers that you get. The method that you have to use to solve it will be the same, but the actual numerical values will be different. So if you type in what I've put, you'll probably get it wrong unless you just happen to hit on the same numbers. Okay, and I had already put that there, so I've already done the answer to that one. Okay, so let's go to the next problem. So the next problem's a two-parter. An alkaline battery is rated at 165 amp hours. It has a maximum current. What is the maximum current it can supply for 15 hours? Well, that one should be pretty straightforward, right? 165 amps times hours divided by hours should give us amps. So let me just copy this one over as well. And then how many days will it last if it is discharged at 1/4 of an amp? Right, so that's a slightly different question, but again, they're all so that's 40, 50 joules. And let's just insert that screenshot. Right, so the first one is just going to be, as I said, 165 amp hours divided by 15 hours, right? Those units are going to cancel, and we're just going to get 11 amps. And the next one is a bit more of a unit conversion, this time in terms of time. So we've got 165 amp hours divided by 0.25 amps, right? So that's going to be a number in hours. So that's 165 divided by 0.25. Right, that's 660 hours. But now we need to the number And this is an example of where you don't need to put the units in for web work. When the units are explicitly put outside the box, then you don't need to enter the units. So we should know that there are 24 hours in a day, right? So if we divide that number by 24, we get 27.5. So we can just continue that and just say 27.5 days. And that was the answer that I entered earlier. We should have stopped doing that. Try that again. 27.5 days. Okay, that was problem 3. Let's continue to the next problem. I'll just submit answers just to make sure I got it right. I did. And here's problem 4. A 48 volt battery pack supplies 42 milliamps of current to a calculator for 20 minutes. Calculate the charge that flows through the circuit at that time. Find the energy in watt hours that the battery delivers to the calculator. Okay, so let's go back here and insert the next picture. Okay, there we go. So again, we've got unit conversions. 48 volts times 42 milliamps gives us the power, right? P equals VI. So the volts is okay, but we want the charge, so we don't need the power. Calculate the charge. Don't need the power just yet. We'll need that for the next part of the question. So we've got 42 milliamps, right, which is, remember, milli is by 10 to the minus 3. So that's 42 by 10 to the minus 3 amperes, which is also 42 by 10 to the minus 3 coulombs per second. Now we've got 20 minutes of that current flowing. So to get the coulombs, so Q is usually the charge, then you just need to multiply, in this case, the time in seconds times the current. And the time in seconds is 20 times 60, 20 minutes, 60 seconds per minute, and then times our current, which is 42 by 10 to the minus 3. So let's see what that brings up in our calculator. So 42 by 10 to the minus 3 times 20 times 60. And that's 50.4 coulombs. Which is what I had before. And now we need to do the energy. So our power is 48 by 42 by 10 to the minus 3, right? To get watts, we need volts and amps, not milliamps. We could go with milliwatts. That would be okay too, but the answer we're looking for here is watt hours, so we need to be in watts. So there's our power in watts, and the energy then is we need the energy in hours, right? Because the unit we're asked for is watt hours. So this is the power in watts, and the number of hours is going to be 20 minutes divided by 60 minutes per hour, right? So it's 1/3. So the answer here should be 48 times 42 by 10 to the minus 3 times 1/3. And let's see if that works out. 48. Right, so 48 by 42 by 10 to the minus 3 by 1/3, and we get 0.672 watt hours, which is what the and again, this one doesn't require us, sorry, it's here, 0.672 watt hours, and because the units are outside the box, you don't need to put them in. Okay, let's go to the next one. So this is a question about the passive sign convention. Remember, if the device satisfies the passive sign convention, then the current is flowing into the positive side. And if it does satisfy the passive sign convention, then it dissipates power. If it doesn't satisfy the passive sign convention, then it's going to generate power or dissipate negative power. Okay, so the first one is asking whether each element is active or passive, right? And the first one is has the current flowing into the positive, so that's passive. B has the current flowing out of the positive, so that's active. C has the current flowing into the negative or out of the positive, so that's also active. And D has the current flowing out of the negative or otherwise into the positive, so it's passive as well. So that's what the selections are. I think you probably get the same answers. And then the power dissipated by element A, right? It is a passive device, so it is dissipating power, so we just have to multiply the current by the voltage. So that's 20 by 10 to the minus 3 times 1, which is 0.02 watts. Element C is an active device, so it's not dissipating power, it's generating power, providing power, so the dissipation is negative, whatever the current times the voltage is. In this case, it's 5 times 4 by 10 to the minus 3 to get us minus 0.02. And I'm not going to draw that one out. That one's, I can just talk through. Let's just submit the answers and check everything's correct. Yep, we're all good. So next problem. Problem 6. Determine the maximum voltage that can be safely applied across a 3.3 kilo ohm, 1.25 watt resistor. So this can sometimes be a problem, right? The resistors we have in the lab are only usually a 1/4 watt or sometimes 1/2 watt. But we can actually generate the power supplies we have can provide much more power than that. So it's possible to make a resistor burn. We try not to, but it's nice to know how to calculate some of the maximum values, and that's what this one's about. Right, so we have two relationships here, right? We have P equals VI and V equals IR. Right, so the maximum power and voltage. So oftentimes we combine these two equations, right? So we can rewrite this equation, Ohm's law, to say I equals V on R. And then we can substitute that into here and say P equals V times V on R, right, which is equal to V squared on R. And that means we now have V squared on 3300. Remember, kilo is by 10 to the 3, so 3.3 by 10 to the 3 is 3300 ohms. And that equals 1.25 watts, because we're given the number in watts. So we can rearrange that and say that V squared equals 1.25 times 3300, or V equals the square root of 1.25 times 3300. And let's see if we can put that into Google. Right, so 1.25 times 3300, is that it? And there's a number, and then we can take the square root of that. Oops. Nope, didn't like that for some reason. Maybe I gotta do the square root. 1.25 times 3300. There we go. Right, it's 64.2. Now, your calculators will give you a ludicrous number of decimal places. You don't need that number of decimal places, right? So significant figures, in your intermediate calculations, use 4 significant figures. Your answers usually only need 3 significant figures. Sometimes web work is very picky, so sometimes you're better off doing 4 significant figures or more, but 4 significant figures for everything. And let's just check that that one's still correct. Yep, that looks good. Let's go to the next problem. Right, a smartphone battery uses a battery that provides 4.8 volts and stores 4.8 watt hours of energy. How many minutes will the phone operate if it draws a constant 36 milliamps from the battery? So now, again, it's a conversion problem. So let's see what Let's put the problem in here. So 4.8 volts, 4.8 watts, watt hours of energy. How many minutes will it operate? So what do we got to do here? We've got our watt hours. So watt hours is 4.8. So one thing we could do, right? So we know that P equals VI. We know that we could convert watt hours to amp hours by dividing the voltage into the watt hours, right? So if we have 4.8 watt hours divided by 4.8 volts, using this, we can say that that means we have 1 amp hour of capacity in the battery. Right, so 1 amp hour. But we're not asking it for an amp, we're asking it for 36 milliamps. So 1 amp hour divided by 36 by 10 to the minus 3 will give us the number of, and that's in amps, right, which we can cancel out, will give us the number of hours. So let's just do 1 on 36 by 10 to the minus 3 back here. (36), not 26. Right, so that's 27.7 recurring hours. And I'm going to use my for significant figure intermediate result. But what we're after is the number of minutes, right? So we have the number of hours. So to get the number of minutes, we've got to multiply hours by minutes per hour, which is 60, which gives us 1,666. And I'm going to round to 1,667, and the unit here is minutes. It's not given outside the box, so you have to give that. Okay, so I can submit those answers, and we're good. And I'm done with homework.